Hello and welcome to a DIY edition of Inside Out Guitar. DIY pedal projects are a great way to learn more about how guitar sounds are created. The Third Man Hardware Fuzz-A-Tron DIY Kit is an entry-level pedal project that comes with clear step-by-step instructions for those interested in building a guitar pedal but don't know where to start. Third Man has a comprehensive build video on YouTube where you can follow along and get helpful tips on building the Fuzz-A-Tron as you go. I've provided a link in the video description to where you can purchase the Fuzz-A-Tron kit and a link to their how-to video. The Fuzz-A-Tron is Third Man Hardware's take on a Mosrite Fuzzrite circuit. One thing that some folks have noted about the Fuzz-A-Tron is that, like the Mosrite Fuzzrite, the pedal does not have an on-off indicator light. This video will walk you through a simple modification of how you can add a LED so you can see when the effect is on and off. The four components that we'll need for this modification are a LED. I chose a yellow LED to stay consistent with the Third Man black and yellow color scheme. A LED bezel, which will be mounted on the pedal enclosure and hold the LED in place. A current limiting resistor, value to be determined. And a triple pole double throw foot switch, which we will discuss in detail later in the video. In the video description, I've included a bill of materials list with Amazon affiliate links, which includes the items needed for this modification, as well as a list of tools that I'll be using to make ordering things easy for you if you need to grab anything. Using these links also helps to support these video productions and keeps the channel going, so it's a win-win. Alright, let's take a look at a layout that I've made of the pedal components. We can use this as a visual reference when we are building this pedal. You'll notice there are a few changes that I've made to the existing design. First, I've eliminated the battery connector because I will always be using an external power supply. Second, we'll be installing an on-off indicator LED that requires a triple pole double throw switch. Third, I've added a 1 megohm anti-switch pop resistor. Next, I've added some ground wires to the input and output jacks. And finally, I've flipped the positions for the volume and tone controls. Flipping the control positions makes the physical layout a little more streamlined, and I personally prefer my tone control on the right of the pedal and the volume on the left. You can do any, all, or none of these modifications. If you'd like to use this layout, feel free to download the PDF of it at the link in the video description. I think it's a great way to visualize all of the connections for the pedal, and it helps to verify your work after each step and check everything after the build is completed. You'll notice that I've simplified the color scheme to yellow, red, and black. Red is for positive voltage, black is for ground, and yellow is for the audio signal. Yellow was an obvious choice for me because it's part of the Third Man brand's color scheme, but you can use whichever color wires you have. One thing I noticed on the Fuzz-A-Tron build document was that there was a small typo on the schematic which conflicted with the information in their instructions. The directions say to connect the T2 lug on the tone pot to the V1 lug on the volume pot and connect the V3 lug on the volume pot to ground. But the schematic shows that V3 is connected to the tone pot and V1 is connected to ground, effectively making the volume control work backwards. No big deal at all, let's just fix the typo on the schematic to save us from any confusion later on. To get started on the build, I've put painter's tape on the enclosure and measured a center point where the LED bezel will be installed. The enclosure is 3 inches wide, so we need to draw a line at the 1.5 inches mark. I found that 1 inch above the top edge of the on-off switch hole is a good spot for the vertical placement of the LED, so place another line there. After those lines are drawn, I used a center punch to create a mark on the enclosure at the point where the two lines converge. A center punch gives the drill bit the ability to bite into the metal a little easier, and the bit won't drift away from your intended hole placement. I drilled the pilot hole with a 1/16 inch drill bit and used a dab of lubricating oil to reduce friction, improve drilling accuracy, and preserve the life of my drill bit. I increased the hole size gradually by using 2 drill bit sizes up in my drill bit set each time until I reached the 5/16 inch bit size. This takes a while, but be patient with this process and you'll get really clean results. After the drilling was done, I used a deburring tool to get rid of any rough edges on the enclosure. Then I peeled the tape off and used a shop rag with some 91% isopropyl alcohol to clean off any residue and shavings. Once the enclosure is cleaned up, it's time to install the LED bezel. The bezel comes with a lock washer and a nut. Place the bezel into the hole, then fit the lock washer on the bezel, then screw the nut on. Be sure not to over-tighten the nut. You don't want to strip it and have the bezel flopping around in there. Let's put all of the hardware in the enclosure now. The power jack, the input and output jacks, and the potentiometers. Again, I place the pots in the opposite positions from where the third man instructions tell you to put them. That's just a personal preference, take it or leave it, but make sure that if you are not using my configuration, remember that the wiring diagram that I've provided is flipped. And finally, let's install the triple pole double throw switch. Now we have to find the right resistor value to limit the current going into the LED. I'm not using an ultra bright LED, so all I need is a low value resistor to get the desired brightness. 330 ohms to 390 ohms works nicely here. If you use an ultra bright LED, it requires a much higher resistor value to bring its brightness down to a reasonable level. You can set up your own brightness test on a breadboard by connecting a resistor of any value to the positive rail and connect the long leg of the LED to the other end of the resistor and the shorter end of the LED to ground. Swap out various resistor values until you settle on the preferred brightness level. This will be your current limiting resistor. Before we do anything with the LED, we need to place the plastic mounting ring over its legs. We'll need this plastic fixture to seat the LED into the bezel later on. After that's in place, we can J-hook the current limiting resistor to the positive lead of the LED. J-hooking is a way to mechanically connect two components. The current limiting resistor needs to be attached to the longer of the two leads on the LED. I simply curl the end of the resistor lead with long nose pliers forming the letter J. Then I do the same thing with the longer of the two LED leads. I interlock the curled end of the resistor with the curled end of the LED lead. Then I secure them mechanically so they can't escape one another. Using my helping hands tool, I hold them in place with clips. Then I solder that connection. It doesn't take much heat or solder to make these connections solid, so don't overdo it. Next, we'll want to J-hook a red wire to the other end of the current limiting resistor. 3 or 4 inches should suffice, but be sure to place the wire in the enclosure to see how long you'll need it to be before you cut it to make sure you have an adequate length. I will often leave a little more length than what I think is necessary as a safety margin. We can always trim it down later. Once the red wire is connected to the current limiting resistor, let's use some heat shrink tubing to cover those connections. I'm going to use red heat shrink because this will be connected to the positive terminal of the DC jack. I'll use my heat gun to shrink the tubing down. Try to direct the heat only at the tubing and away from the plastic mounting ring, as you can accidentally melt the plastic and deform the ring. And don't apply too much heat, only enough to see the tubing shrink, not melt. Next, let's attach a black wire to the negative lead of the LED using the same J-hook process as before. The black wire can be 2 to 3 inches long, but again, check the distance from the LED hole in the enclosure to the Footswitch top-middle terminal. You can use the layout diagram here as a reference. Curl the ends of each lead with long nose pliers, interlock them, solder them, then add heat shrink tubing to cover the connection, and apply a little heat from the heat gun. This time I'm using black tubing as this lead will be connected to ground. Now that the red and black leads are connected to the LED, I'm going to mount the LED in the bezel to make sure that the lead lengths are adequate. If the leads don't reach, we'll have to do it again, but in this case, everything looks great. I left the leads long just to be safe, so there's a little too much right now. I'll give them a quick trim. Then I'll bend them into place and connect them to their respective components. In this case, the red wire is going to the positive terminal on the power jack, and the black wire is going to the top middle terminal on the foot switch. I'm not going to solder these into place quite yet. Next, I'm going to start connecting some of the components in the enclosure. You can reference the layout diagram I've provided and come up with your own order to do these connections. The first connection I'll make is the T2 lug to the V1 lug. Then I'm going to run some of the ground connections using black wire. All of the black wires are connected to each other to form a ground connection that terminates at the power jack. I like to hook the wire around the terminals on the component for a solid mechanical connection before soldering them. One little hack that I do is using painter's tape to hold the wires to the PCB when I'm soldering. Now let's talk about the on-off switch. The switch that was included with the Fuzz-A-Tron kit is a double-pole, double-throw switch. This means there are two columns of terminals that can connect in two ways internally depending on which position the foot switch is in. How a foot switch works is more easily visualized using a single-pole, double-throw toggle switch, so let me show you that first. Here's a common toggle switch that we've all seen before. It is a simple two-position switch. When the switch is flicked in one direction, the center terminal connects to one of the outer terminals internally. In this position, the center terminal connects to the top terminal. When the switch is flicked in the other direction, the center terminal disconnects from the top terminal and connects to the bottom terminal internally. Because we can't see the physical connection inside the switch, we can test these connections with a multimeter in continuity mode. With a switch positioned like this, we can hear a signal because the probes on the digital multimeter are touching the two terminals that are internally connected, thus creating a circuit. When I flip the switch, my multimeter stops beeping, indicating those same two terminals are no longer connected internally. I'll now connect the probe of my multimeter to the terminal on the opposite side of the switch, and the beeping resumes, indicating that these two terminals are now connected internally. Note that the outer terminals do not internally connect to each other. They can only connect internally one at a time to the center terminal. Instead of using a toggle switch for turning the effect on and off, pedals like the Fuzz-A-Tron use a foot switch, which changes between these two connection configurations by simply pressing down on the button rather than flicking a switch. Internally, they are accomplishing the same task. A double-pole, double-throw foot switch has essentially two single-pole, double-throw switches placed side by side in a single component. They are two discrete columns that internally do not connect laterally, only up and down. Like before, in one position, the two center terminals are connected to the two top terminals internally. When the switch is pressed, just like we saw with the toggle switch, the center terminals internally disconnect from the top terminals and connect to the bottom terminals. Typically, pedal designers use the terminals on the left side of the foot switch to route the input signal because those are the closest to the input jack. And similarly, the terminals on the right side are routing the signal output because of their close proximity to the output jack. Because we're implementing a LED into this design, we will need a third column of terminals dedicated to turning the LED on and off. This is where using a triple-pole double-throw switch becomes necessary. A triple-pole double-throw switch is essentially three single-pole double-throw switches side by side housed in one component. This now gives us three discrete columns of three terminals. I'll still use the terminals in the left column for the input and the terminals in the right column for the output, but now I can use the terminals in the middle column for the LED switching. So how is this going to work? Well, in order for the LED to function, it must have a positive and negative connection. We'll be connecting the anode side of the LED, that is our red wire, to the positive terminal of the power jack in this design. So the positive side of the LED will always be connected. If we connect the black LED wire to the top terminal of the middle column on the foot switch, and we connect the center terminal of the foot switch to ground, the switch will internally connect the LED to ground when the switch is in the on position, and it will illuminate because it has both positive and negative connections, thus forming a circuit. When we hit the switch again, it will disconnect the LED from that ground connection, breaking that circuit, and it will go dark. Simple and, well, pardon the pun, effective. Okay, let's get to work putting this together now. Let's wire the effect bypass part of the switch. It's a good practice to ground the circuit input signal when the effect is in bypass. So let's use a wire clipping from one of the components leads that we trimmed off earlier and connect the top left terminal to the unused bottom middle terminal. Remember, the center terminal will be connected to ground, so when the switch is in the off position, the middle bottom and the middle center terminals will be connected to each other. This will send the circuit input to ground, completely shutting down any input to the fuzz circuit. We will use another wire trimming to connect the bottom left terminal to the bottom right terminal on the foot switch. This will route our guitar input signal directly to our output jack when the switch is in the off position. This is known as true bypass. Now I'm going to connect the input jack to the middle terminal in the left column of the foot switch. This is our guitar signal entering the foot switch. Then we'll connect the middle terminal in the right column to the output jack. We'll be using the top left and right terminals on the foot switch for our PCB input and output respectively. The output of the fuzz circuit is the middle lug of the volume control, labeled V2. We'll run a wire from that middle lug to the foot switch. Connect that wire from V2 to the top terminal of the right column on the foot switch. I'll connect the top terminal in the left column to the PCB pad labeled in. This means that when the foot switch is in the on position, our guitar signal will go into the fuzz circuit. This gives us a completed effect signal path. I also added a 1 megohm pull-down resistor at the signal input to get rid of any potential switching noise. Sometimes effects can have a loud popping sound when switched on and off if they don't have a pull-down resistor. It's super cheap and easy to install, so I put one in by connecting one end of the resistor to the top left terminal of the foot switch and the other end of the resistor to the center terminal, which again will be connected to ground at all times. Now that the circuit work is done, it's time for the first test. Notice that I didn't bother putting the control knobs on the volume and tone pots at this stage because if there are any issues related to the pots, I may have to pull them out. This could save me a little time and energy. So here we go. Let's plug the pedal into a 9-volt centered negative power supply and see if the LED lights up. Awesome. The first test is a success. Next, let's see if there's any signal going through the pedal. You can simply connect your guitar to the input and connect a cable from the pedal output to an amp, but I've got an oscilloscope here where we can see the signal on a screen. Let's see the effect in bypass to make sure that we are getting a clean signal with the effect off. The blue waveform on the screen is the test signal that we are using for our reference waveform, and the purple waveform is the signal going through the effect. You can see that they look identical, so the true bypass foot switch is working perfectly. Now let's engage the effect and wow, look at that radical waveform. This is with the tone control on 10. The Fuzz-A-Tron is destroying that 1 kHz sine wave in the most awesome way. Cool. Looks like we've got a functioning fuzz pedal here. Let's dial back the tone control to see what happens to the waveform. Well, look at how the waveform flattens out as I turn the tone control down. This is almost exactly at the halfway point on the tone control. Let's keep going. Now I'm turning the tone down all of the way, and we get a third unique waveform profile. Nice. And here it is again with the tone control maxed out. I think it's fun to see what an effect does to a sine wave because this is literally visualizing sound for us. Another way of visualizing what the effect is doing is to look at a 1 kHz sine wave on a frequency spectrum analyzer. When the effect is engaged, we can see the 1 kHz fundamental hasn't changed, but now there are harmonics of that frequency being created by the effect. The frequencies that are even mathematical multiples of the fundamental frequency, like 2 kHz, 4 kHz, 6 kHz, 8 kHz, etc., are called even order harmonics, and the frequencies that are odd mathematical multiples of the fundamental frequency, like 3 kHz, 5 kHz, 7 kHz, etc., are called odd order harmonics. Even order harmonics are thought of as being quite pleasing to the ear, whereas odd order harmonics are a bit harsher. This circuit has a solid mix of both, so this gives us a little insight as to what to expect when we put a guitar signal through it. A third way to visualize what we hear is to send pink noise into the effect and look at the results on a frequency spectrum analyzer. Pink noise is random noise produced at the same energy level for every frequency in the audio spectrum. So here's what pink noise looks like on a frequency spectrum analyzer. When I engage the effect, you can see that the frequencies below 500 Hz drop drastically and the frequencies above 500 Hz increase. This gives us yet another insight as to what the pedal is doing to our sound. In this case, we can see which frequencies are being emphasized or de-emphasized when the effect is on and the tone control is at 10. Alright, let's finish the pedal now. We have knobs to put on the pots and stickers to place on the enclosure. It's a good idea to give the enclosure one more wipe down with that shop rag and isopropyl alcohol after all of that handling to make sure you have a clean surface for your stickers to attach to. You can also put the back plate on now, and if you want to use the rubber feet they included, go ahead and put those on the bottom of the plate. I'm going to put a couple strips of hook and loop on it later, so I can get right to the playing portion now. I'm going to try this pedal out with a few different guitars, a few different amps, a few different mics, and record it all for you. So here you go. Enjoy. Thanks so much for watching. I hope you gained a little more insight about guitar electronics and guitar tone with this video. If you like learning about guitar, please check out my other videos as well, and be sure to like and subscribe so you can catch the next thing that I do.